I'm getting very quick at things. It's like, all right. Okay, so I guess we only have, after this lecture, I guess there's only like 6 more lectures left. So trying to plan things down towards the end of the semester. So the first thing I like to do is I need to correct a statement. So let's look at that.
They got a big truck. Got the tree down, and then one saw and cut that tree down, and the tree fixed on, and here it was like. Down.
All right. Okay, awesome. Okay, better now.
That's quite.
Okay, so let's go back to the notion of strong linkage. All right, so I just wanted to be a little bit clear about this. So we have 2 categories that we're sort of dealing with. So one is in GRT, and this is where we actually do have something called strong linkage. And then we have the GR category. And that category, we just have the notion of what's called linkage. Because we really don't have an ordering on the weights in the GR category. So linkage is the best we can really do. So I just want to restate these theorems and kind of explain sort of what we did. So the first statement is the following. So if lambda and mu are just weights, and if I take the module ZR lambda with LR hat mu. Now, let me just be a little bit more clear about this. Remember, this is in the GRT category. Okay, so we're looking at things in terms of GRT composition factors. So suppose that this is non-zero, then mu is strongly linked to lambda. Okay, so we actually proved that last time using this sort of idea of good heat filtrations. Okay. And strong linkage in the G category. So 2 is suppose we have 2 weights, lambda and mu, x of t. So if this is the place where I wasn't like really clear last time. So suppose that this is non-zero. Now, these are not, when I mean this, I mean in the GR category. Okay. So we're looking at that as GR composition factors. So then we can't really say things about strong linkage, but we at least know that we have linkage under the action of the extended affine Wildberg. Okay, so let me show you the difference. All right, so this time I'll have to use my A2 picture here. Okay, so this is minus rho here. Okay. So this is the P minus 1, P minus 1. All right, so this is the restricted region, X1 T. Now, if I take this weight up here, lambda, and if I look at E1 lambda, then it turns out that this will have a composition factor L1 lambda hat, and it has one which is strongly linked down here. So we have mu, we have L1 hat. This turns out to be not equal to 0. So there's an affine reflection, which actually goes down, and it turns out that that is not a 0 too. Now, it turns out that C1 hat lambda has, turns out, I believe, 6 composition factors. Okay, so it has P1 T mod. Okay. Now, it only has 2 of them which actually lie inside the restricted region, namely L1 hat lambda and L1 hat mu. And the rest of them live sort of outside the restricted region. Okay. All right. Now, let me draw you another picture where we look at the G1 composition factors. So I'm going to draw the restricted region again.
Which root system did you say this one?
This is A2. A2 root system. Okay. Now, if I take the same module here from lambda, okay, so instead of putting the hat on, I just take ZR lambda. Okay. So it turns out, and let me just kind of draw it in purple here. So it has another composition factor down here. Let me draw it in orange. So we have another composition factor down here. So that kind of coincides to this mu. And this also has 6 composition factors. And we know that the irreducible representations are indexed by things inside of X1T. Okay. So this also has 6 composition factors. As one module. Okay, so we're sort of forgetting the grading. And those composition factors live sort of like here. Okay. They're actually, you actually can reflect across here and then pull things back under the action of the affine valve. That's the point. So these are the 6 composition factors inside of this module ZR. Okay, any questions on this? Okay, so again, because of the T action, we have to go outside the region. which actually has some advantages. Now, when I restrict this down to GR, then I just get this picture over here. Okay, because if I have something down here, I can just pull it back into this region and those two identify. So I just wanted to show you the difference between the two categories. Okay, any questions on this? All right, now just like with the GR category, we could look at extensions in the GRT category. So let's look at extensions. So let lambda and mu be an x of t. All right. Now we can use the Chevrolet anti-automorphism. All right, this is just a fancy way of saying it's a transpose, right? Because in GLN it's just a transpose. Just take the transpose of the matrix. Okay. And the transpose dual, you get the following. X1 GRT of two irreducible modules. X to R0. This is true for any xj. Okay. So with the transpose dual, we saw that we can actually flip the two. Okay. So if you take an extension between these two modules, you can apply the transpose dual, and it'll just sort of flip the extension around. So this is going to be equal to xj gr r not mu. It's the same proof as in the G category. And this works for any j bigger than or equal to 0. Okay. Now, it turns out that we can compute or recover information about extensions in the GR category from the GRT category and vice versa. So if I want to know, let's see, xj of GR of two irreducible modules without the hats. Okay. All right, now we know that T acts on this. So the torus acts on this, on the extension groups, because the modules are G modules. So you can actually put an action of the torus on there. So we can actually write a weight space decomposition. So this has a weight space decomposition. So this is gamma in x of t of xi gr r lambda r mu, and then the gamma weight space. Okay. All right, now this is going to be the same as looking at all these things. I sort of move it in the GRT category. So, okay, so these are restricted weights, so I can just, so these, the lambda are restricted, so I can get rid of the R's. So I can just bring this in on inside. Because to get from here to here, you're just taking the fixed points under the torus. You can just bring this in. Okay, now I know that we have the TRX, but then T sub RX trivial. So this weight here has to be of the form P times nu. Okay. And so what we get is we can write this out now as all nu in x sub t of xi. So we have this formula. We'll stare at it in a second. Let's put this on, on the inside. Okay. All right, so I should probably keep the views here and put the house back in just to be sure. Okay, so that's a better way to say it. Okay, so the point is that if I take an extension in the GR category between two irreducible representations, I can actually compute it by just taking one of them and then taking translates of the other one under PDDR, computing it in the GR category, computing it here, and then I can get the answer up here. Okay. So you can actually go back and forth between figuring out extensions. So if you know extensions in the GRT category, you know extensions in the GR category. Okay, so that's point number 2. So I don't know, maybe I should say this is number 1. It's formula number 2. And then I have another point. So just like you can look at X1s and compute them in the second Stockholm second radical layer, you can do that here too. So if I want to know, I guess this is great. So if I want to know X1 in the GRT category between two irreducible representations, I need a condition on the weights. Remember, lambda is not smaller than mu in the weight order. Okay. So if this is true, then what I can do, sorry, it's the HOM. It's HOM GRT, the radical in the GRT category of Z hat R lambda L R hat. Okay, so the second radical layer, so the radical mod radical rad 2 will actually determine the extension information. So this is just like that result we proved for G modules. Same proof. Okay, and then finally point number 4. So let lambda mu be x of t. So if x1 RT R hat lambda at mu is not 0. Okay. So if it's not 0, then we could either, by this over here, we can either look at this or we can look at that. Right? Which means that we can always put it in the situation where lambda is strictly less than mu. And so if this is not equal to 0, then what must be true? Well, that means that this is not equal to 0. That means that this has to be a composition factor of ZR at lambda. and that means it has to be linked. So then lambda has to be in the orbit. Okay, so it's just like the strong linkage statement for the H zeros. Exactly like that, and for the vial modules. Okay, any questions on this? All right, so the next thing I want to do is I want to talk about a very, very special module. This module comes up in representations of reductive groups all the time. Whether you look at finite reductive groups or whether you look at sort of one where the group is infinite. And so this is called the Steinberg module. So let me just draw you a picture. Okay, so this is the A2 picture over here, minus rho. So the point is that at certain vertices, nice things happen. So for example, at this vertex here, this is P minus 1, P minus 1. And so if I take the representation corresponding to this, L P minus 1, P minus 1, L P minus 1 rho. Remember, rho is the sum of the fundamental weights. It's also half sum of the positive roots. So this is called the Steinberg representation. And we sort of label it as ST1. Okay, so it's the first Steinberg representation. Now, if you want to go up to the next Steinberg representation, all you do is you just increase P by P to the R. Okay. So the definition of the Steinberg representation so let me just write it out. So definition. The arc Steinberg representation is L P to the R minus 1. Okay, it's that irreducible representation with that particular highest weight. All right. Okay, so now if you look at this one over here, then what are the composition factors of this? They have to be strongly linked. But there's nothing which is dominant, which is strongly linked to this thing except itself. So this shows that it's irreducible. So, and if I take H0 of P minus 1 rho, well, my strong linkage, it has to be irreducible. And it also has to be equal to the vial module. And it also has to be equal to the tilting module. So at this vertex, everything sort of just coincides. And so the same thing actually is true for this one too. So this is a fact which doesn't take, it's not that hard to prove, right? It's basically saying that if I take the Arth Steinberg representation, this is the same as H0 P R minus 1 rho, and it's also equal to V R minus 1 rho also. Okay. Now, we also know something about what happens with disease. So here's another fact too, is that if I take the Z P to the R minus 1 rho, Might as well put a hat on here. Okay. And if I restrict this down, so this is a GRT module. So this is also isomorphic to the Steinberg representation. Let's go restrict it down to G. Okay, so at this vertex, a lot of, everything just sort of collapses. And the modules are all the same. Highest weight modules are all the same. Okay, so the next thing I want to show is the following thing. Now you think that this is kind of special. There's even something more special. So the Steinberg module. I'll show you something even more cool in a second. So the Steinberg module is injected and / projected as GRT module and also as GR module. Okay, now we know it's a GRT module, and we've actually proved that if it's projective over GRT, it's if and only if it's projective over GR. So we only have to prove one of the statements. So it suffices to prove. So let me just start a proof. It suffices to prove STR. Let's see, I guess which way we're going to do it. Take a look at this. I guess we'll just prove it's projective. It's projective. Over GR. GRT, I guess. So once it's projective over GRT, we know it's projective over GR. It's one of them. Okay, so this actually is not too hard. Okay, so note, so let R half mu be a simple GRT model. And I want to first look at X1 GRT with respect to the Steinberg and LR half mu. Okay. So we basically want to show that this is going to be 0 for every single simple module, and then we know that Steinberg R is projected. Okay. All right, now we already know a case of this. So remember, this is going to be equal to LR hat P to the R minus 1 rho. Right? So so here's case 1. So suppose, let me just say it this way. Okay, so suppose that P to the R minus 1 rho is not strictly less than mu. Okay. So then we know this is Hom GRT. Well, the radical of this is irreducible already, right? So the radical is going to be 0, right? It's the radical is the largest module such that the quotient is semi-simple. Smallest module such that this is semi-simple. So this is going to be a 0 here. It's the radical. This is irreducible, right? This is LR. Yeah. All right, so obviously, homomorphism to the zero moduling is something like zero. So we're okay, right? So that's under this assumption over here. Now, if we don't have that assumption, we can flip things around, okay? So otherwise, we need to look at X1 GRT of LR at mu Steinberg R. Okay. And again, we know this is Hom GRT radical of CR at mu into Steinberg. Okay. Now suppose that this is non-zero. Well, suppose that this is non-zero. Well, this is irreducible, so that means that the radical of ZR hat mu has to surject onto the Steinberg. Right? Steinberg is irreducible, so I mean, it has to surject onto the Steinberg. That means the dimension of the radical here has to be bigger than the dimension of the Steinberg. So the dimension of the radical of ZR hat mu must be bigger than or equal to the dimension of the Steinberg representation. But the Steinberg representation here is a baby Burma module, right? So this has dimension p to the r times the number of positive roots. Okay. We also know that ZR hat lambda has the same dimension. So this has to be bigger than this, but we also know the radical of ZR hat mu. Let me say it this way. So, but the dimension of the radical has to be less than the dimension, strictly less than the dimension of ZR hat mu, which is also equal to PGR times. Okay, so this is clearly a contradiction. So we have that X1 GRT of this thing here, Steinberg R, LR hat mu. Okay, so that shows the projectivity. Okay, so we're done. And if you want to show injectivity, you can just reverse the roles of LR lambda and Steinberg. Okay, any questions on this? So Steinberg's always an irreducible representation for G and GRT, also GRB, and when you restrict it down to any of these categories, the GRT category or the GR category, it has to be a projective module in that category. Okay, so I promised you that I would show you something which I think is pretty neat, and I still don't understand this. Okay, so. All right, so I introduced the notion of P filtration. Okay. So let me mention a conjecture. So I was actually fortunate enough to be at MSRI back in 1990. It was the second conference that I ever went to. And that's where this conjecture was actually stated first. So this is a conjecture due to Steve Donkin. It was stated at MSRI in 1990. All right, so it says the following. So let M be, let's say, a finite dimensional. Keep it simple. G mod. Okay, so G is a reductive group. Okay. So the conjecture says the following. M has a good PR filtration. Okay, so I defined PR filtration for you. This was a filtration where you had sections of the form L lambda tensor H0 lambda twisted. Okay, so I defined PR filtration. So this happens if and only if Steinberg tensor F. So I take the R Steinberg and I tensor by F. This has a good filtration. You know what a good filtration is? It's one where the sections are the form H0 lambda. This is a pretty amazing conjecture. You have a module and you want to test whether it has a good PR filtration or not. You can just take this sort of magical module, you take the tensor product of it, and you just see whether it has a good filtration. Okay. All right, now since this time, we actually found counterexamples to this. So let me say what we know about this. So this, I'll self-promote a little bit. So this conjecture kind of was sort of left alone for a long time. And there was work that I did with Tobias Kilderthon, who was here in Georgia as a PhD exchange student. So this is sort of work with Kilderthon. So, this is around, let's say, 2015. Okay. And then later on, this is also work with Bendel. Actually, myself. Paul Savage, who was a postdoc. And this is from like 2018 on. All right, so notice that this is an if and only if statement. Okay. So there are two directions in this. So there's the forward direction, I'll just write it over here. So there's the forward direction, and then there's the opposite direction. Now, the forward direction you would think of as being somewhat innocuous, but it turns out that it's not. And this is an open conjecture which we would just love to know the answer to. So let's call this conjecture something. Let's call this D-filled conjecture. So we sort of refer to this as the the Duncan PR filtration conjecture. Actually, I should let me just call it D-fill. Yeah. All right, so it turns out that if I take D-fill in the forward direction, so M has a good PR filtration, implies Steinberg tensor M has a good filtration. This statement is equivalent to the following. Okay, so it's equivalent to the following statement. It's equivalent to L lambda. Let me say this one. It's kind of stated this way. It's equivalent to Steinberg tensor L lambda has good filtration. It turns out this doesn't always happen. But the conjecture is that it happens for restricted weights. This time I've been working up to being able to state this in this class, right? Okay, so this is the statement. So in order to prove this statement here, which involves infinitely many modules, you just need to show it for finitely many modules, namely the modules which are actually in the restricted region. That Steinberg tensor L lambda has a good filtration. Okay. All right, so what's the status of this? So the status is that we think this will hold for all P. So the conjecture is that E field in the forward direction holds for all P. I talked to Steve Duncan about this about 2 years ago, and he thinks that this might be true. What do we know about this? So we actually proved that it holds for all rank 2 groups. So BN, PS show, and also with work that we did, showed this holds for all rank 2 groups. Okay, so for B2, G2, A1 cross A1, all rank 2 groups, it holds. And we also showed it holds for all primes like for A3, for example. So there's a lot of evidence that this is going to be true. So you want something to really work on. This is, you know what this is, you know what this is, you know how to take tensor products, you know what a good filtration is. I gave you criteria to show, and when something has a good filtration, you just need to prove this. All right, so we think this is going to unfold for all. Now, much less is known about the validity of the other direction. So it turns out that B filled in the other direction actually is not true. Okay. So let me give you a counterexample. This is due to us. So yeah, I think this was the first counterexample. We found this about a year ago. So BNPS like 2019. Okay, so this paper just, well, we found it a year ago, but just got published now. So this is incredible. Okay.
This is the E8 example, right?
No, this is a G2.
Oh, GT.
Yeah. So it turns out that for for the root system being G2 and P equals 2, there exists some H0 lambda that does not have good duplication. Okay, so why is that a counterexample? Well, if I take an H0, my tensor with Steinberg, it always has a good filtration. Okay, but it does not have a good PR filtration. So as long as you find an H0 that doesn't have a good PR filtration, it's a counterexample to the other.
Is the only red cube group, or maybe most cube group, or example like this? Or?
Well, that's a good question. So actually, we have more counterexamples now that we're actually working to write up. You guys are maybe the first to know this. So, anyway, there are more counterexamples out there, and so this is going to be related also to something that I'll call Donkin's tilting module conjecture, which we call D-tilt. Okay, and it turns out that D-tilt and D-filter are related. So I need to actually give you more information about tilting modules to state that conjecture. But I can state this conjecture with, we'll be done with that. Okay, so it would be really nice to know like how true this is. Is it true for P bigger than 2H minus 2, for example? And that would be really nice. And this is also related to what the Partial and Scott did also, with showing that when the Listic conjecture holds and P is bigger than 2H minus 2, these guys have good PR filtrations.
So what's the strategy in these two papers? You just sort of brute force check that these things, that's
Yeah.
what's criterion? Or?
That's another good point. So the thing is, we thought it was going to be true. We thought, okay, we'll prove the tilting module conjecture, or the tilting module conjecture. This statement here are closely related. So we're trying to prove it, and then all of a sudden discovered that we don't think it's true anymore. And that's how we were able to get the counterexample. It actually wasn't too hard to prove this.
No, but I mean, default in the forward direction, like up to rank 2, is it just sort of like brute forcing a bunch of calculations, or what's the strategy there?
Yes and no. I mean, so it's true. This is true. There's a general proof for P bigger than 2H minus 2. You read the papers. This has a lot. So it turns out that we actually proved this. It's actually true for P bigger than 2H minus 4. We've actually lowered it a little bit. So generically, it's kind of true for that bound. We don't even know if it's true for P bigger than H, for example, in general. So there's a general way to prove this for larger primes. But then for smaller primes, we have to use various tricks to actually prove this. So if you go back over here in the statement, if you take like fundamental weights, as long as you're not in E7 or E8, we can prove this statement for every single fundamental weight. So E7 and E8 for P equals 2. For certain fundamental weights, we don't know how to do it yet. But for every other prime and every other fundamental weight, we actually know this is true. And that's also in this paper that we have. So. Yeah, we think it's really sort of, it's sort of old school, but there's definitely new techniques that are needed to sort of understand this problem. And I think it's certainly related to knowing like characters of irreducible representations just a representation theory in general, of reductive algebraic groups. Okay, so if you're interested in like, in something which is still open, this is definitely, very much open. Okay. So what we're going to do next, meantime, let me just kind of give you an outline of how the rest of the semester, I envision the rest of the semester. All right, so on Wednesday, I want to finish off the GRT category business. We're going to show it's a highest weight category. So we're going to show it's a highest weight category. Well, I should be a little bit careful. Sort of not necessarily in the sense of, well, I guess it may be in the sense of Clamp, Marshall, and Scott. The difference between this category and like category O is there are infinitely many irreducible representations. Okay, so it's kind of it behaves a lot like the highest weight category. It may not be formally the highest weight category, but it behaves a lot like the highest weight category. So in order to do that, I have to define the standard modules, and I have to define the co-standard modules. So those would be the baby Roma modules and the induced ones and the co-induced ones that I defined before. And we'll have to do some sort of X vanishing result and blah, blah, blah. The same sort of thing we did with G modules. And then there's a reciprocity law too. And so that's what we're going to do for probably Wednesday, maybe Friday too. So Wednesday might carry to Friday of this week. All right, and then what I want to do is I want to introduce the idea of injective GRT modules. And this is going to go back to work of Verma and Humphreys. So we're going to look at things involving results of Verma and Humphreys on what's called we call it the lifting conjunction, which is still unresolved. And so I'll just say it in words. Basically, the idea is that if you take an injective GRT module, you ought to know whether it lifts to a structure of a G module. Does it actually come from a G module? Now, there's something more specific which sort of prescribes the answer. And this is Dawkins' Topi model conjecture. Called detail. There's a really beautiful relationship between D-tilt and D-filt, which I think I'll just state right now. All right, so this is due to this is fairly recent. So this was due to Tobias and myself, and also Sabaja. It's a work he did at Georgia. All right, so this D-tilt was also stated in MSRI. This was also from this famous conference at MSRI in 1990. So it turns out that if you take D-filt in both directions, if and only if. You know that D filled holds, then D tilt holds too. I haven't stated what the tilting module conjecture is yet. And then, as long as you know D tilt holds, then forward direction of the filtration conjecture. So that we call this a hierarchy that we kind of were able to find the connections to. And it turns out that understanding these relationships was just essential to sort of finding a counterexample of this conjecture. So, yeah, so the thing is, sometimes it's instead of just kind of looking at one conjecture, it's not such a bad idea to understand the relationship between various conjectures and various ideas. So, okay, so that's kind of the plan for the rest of the semester. Okay, so let's stop here and we'll continue on Wednesday.